Now we will start studying of real nature of micro objects, and first we will consider wave properties of particles. Wave properties. When we considered light, we started from the statement that light has dual nature. Sometimes it behaves as wave and sometimes as a particles, flux of particles. French scientist Louis de Broglie he mentioned that there was a lot of attention paid for the duality of light, and he suggested idea that dual are all micro-objects, not only photons, and the waves are specific for light, but for particles there are also some waves which are attributed to particles, and the idea, his hypothesis was that particles have a dual nature in a manner which resembles that for photons. If we look at photons, then for photons we have energy E is h omega, and moment is 2 pi h over lambda. Then de Broglie's wave is constructed for a particle from these relations similar for photon. If momentum is for photon is 2 pi h over lambda, for particle with momentum p, the wavelength lambda, the wave, is 2 pi h over mv, where m is mass of particle and v is velocity. And this wave has a frequency which is derived from the first equation. If for photon E is h omega, then for particle with energy E we can attribute the frequency omega is E over h. So these are wave characteristics of Louis de Broglie's wave. As far as this was just a hypothesis, then as we know, only experiment can support it or reject such a concept. The corresponding experiment was performed by American scientists Davison and Germer. These two scientists performed an experiment which supported this idea. The experiment consisted in scattering of electrons from the surface of a crystal, electrons were accelerated to some energy and were registered at some angle. So electrons were emitted in this direction and registered this direction. We remember similar if this is a crystal with a cubic system. We remember that for X-rays the condition for maximum was 2d sine theta is equal to n lambda, where n is 1, 2, 3 and so on, and d is this distance between atomic planes in a crystal, and theta is this glancing angle. This was derived as Bragg's formula, if you remember, and it appears that if we accelerate electrons to some energy, and consequently this corresponds to some momentum mv, and then electrons have some wavelengths according to the Broglie hypothesis, and maximums should be observed at some angles theta when this angle corresponds to this condition. And it appeared that indeed this condition defined maximums in scattering of electrons, and even wavelengths corresponding to maximum could be derived from this equation. You see that this maximum corresponds to some lambda, and lambda depends on velocity of electrons which were accelerated. Thus it was confirmed that indeed electrons have these wave properties. Another experiment was performed by Thomson, and this was a scattering of electron beam on a foil, and when the scattering, if we look at here electrons which scattered on the atoms in the foil were registered on a photoplate here, and if we look at this photoplate, what was observed, there was a picture which resembled a picture of a diffraction on disks, and atoms served as disks. So there were around each of the atoms there were light and dark rings. So again it was confirmation that electrons behave as waves. A very important question is whether this wave properties belongs to electrons flux as an ensemble of electrons as a whole, or this wave properties belongs to each electron individually. This was checked by another experiment which was performed by Russian scientists. You can find their names in Savelyev book. Sushkin, Fabrikant, and somebody else, I forgot. Biberman, Sushkin, and Fabrikant are three Russian scientists. What they made, they repeated such an experiment, but they made it with intensity of electrons so low that in each moment of time only one electron could be found between foil and plate. So in this case it was possible to say whether these wave properties belong to each of electrons or to the flux of electrons as a beam of light, for example. And it appeared that these wave properties can be attributed, so they not can be, but they are attributed to each of electrons. It is a property of each electron. When we try to understand what is happening at such micro level, we cannot make any object, any model which could describe adequately what is happening at micro level. The point is that there is no way to look inside such a micro scale, and any model which we can imagine, this model is inevitably is macroscopic. So it consists of macroscopic objects which obey classical physics laws, and this means that we can just believe in formulas, believe in equations which describe what is physics at this micro level, but it is not possible to build a model like some visible parts of atom. Any model which we build is inevitably is somehow inadequate to reality at this level. It is very inconvenient for people to perceive such physics at this level, but we have no choice because it is not possible to go inside this small volumes, some small scales, and to see how it is working in this level. So if you think that it is difficult only for you, you are wrong, because actually nobody understands how it happens. We only know that indeed this happens, and all that we know about micro world is supported by this theory. By the way, if would this theory be wrong or inadequate, you will have no mobile phones, and all the electronics which we use nowadays is based on quantum mechanics. So it definitely is correct, but the problem is that as far as it is not so visible, we cannot look into atoms, cannot look into these objects which we describe by equations and by these concepts which we now try to study. Now let's consider some single particle which has momentum p and energy E. Such a particle can be represented by a plane wave of the form psi of r t is psi 0 E minus I over H E t minus PR. Indeed, it corresponds to usual wave, which, if you remember, here is E and I omega t minus KR. So if you substitute, this is omega. If you substitute omega from here and k through lambda, you will obtain this formula. Now, let's try to derive what is the group velocity of the de Broglie wave. Group velocity, which we denoted by u, is d omega over dk. So if we take this derivative, we obtain that omega is here, k is here, so it is dE over dP. Indeed, look, from this and that, omega from here and k from here give us dE over dP. Then we can substitute for E its value from relativistic theory. This is P squared plus mass of rest, C squared, M squared, C squared over dP. After differentiation, we have Cp over square root P squared plus M0 squared C squared. That is C squared P over E. Indeed, E is this, so if we multiply this and that by C, here is E, here is C squared. And this is equal to C squared and P, we substitute mv for a particle over, and E is mc squared, where m is relative mass, of course. And result is that group velocity is just velocity of particle. So group velocity of the de Broglie wave is equal to the velocity of a particle. Now let's look at the physical meaning of wave function. This psi is called wave function, and let's look on the, for example, for diffraction phenomena from 2 points of view, from wave and particle, corpuscular. When we look at photons, then in maximum of diffraction, in diffraction maximum, we have that intensity, we have amplitude maximum, in which corresponds to maximum, and intensity corresponds to a amplitude squared. And from the corpuscular point of view, intensity is proportional to number of photons which reach screen at given moment in unit time. Then the interpretation of this psi function, which is wave function, is that for particles, generally it is complex function, so this function multiplied by element of volume dV gives probability to find particle in this volume. Again, if intensity is proportional to amplitude, and this is amplitude, and proportional to amplitude squared, and on the other hand, intensity is proportional to number of particles which reach a given point or given volume. So it is natural to interpret this square complex of this complex function multiplied by this volume as a probability to find a particle in this volume. Now the question arises how to find this function which describes the state of micro object in quantum mechanics. The answer for this question is in Schrödinger equation. Schrödinger was German scientist, so we pronounce this like Schrödinger equation. Well, Schrödinger equation. First of all, we need to state that as any new equation in physics, it cannot be derived from anything. For example, if we compare with classical mechanics, Newton equations are not derived. They are just reflects effects which are observed. The same with Maxwell equation. Maxwell equation and electrodynamics were not derived. We just summarize all observable facts and said that okay, they are described by Maxwell equations. The same with Schrödinger equation. Actually, there was some hint. We will consider this hint a little bit later. First, we will state that for microparticles, the state of microparticles, of any microparticle, is described in quantum mechanics by wave function, which are a function of coordinates and time, and it can be found by solving of the following equation, which is actually Schrödinger equation, minus h squared over 2m. This is Laplacian operator, psi plus u psi, where u is potential energy, is equal to I. It is imaginary unit, h d psi over dt. So this is a Schrödinger equation. If u, potential energy, again this is Laplacian, if u does not depend on time, then psi can be presented as psi of x, y, z, t as e minus I e over h t, and psi on x, y, z. This means that we separated the coordinated part of function and timing part of the function. If we substitute this function in that equation, we will obtain the following: minus h squared over 2m e minus I e over h t and Laplace psi plus u e minus I e over ht psi on x y z equal to minus I e over h e minus I e over h t I h psi of x, y, z. Well, we have cancelled all this e, and then we have an equation that Laplace psi of x, y, z plus 2m over h squared e minus u psi of x, y, z is equal to 0. This is an equation, Schrödinger equation, for stationary states. You remember this, actually it corresponds to Bohr's stationary orbits. So when particle is in some state, so in classical mechanics, if it is in some movement on orbit, so this is movement. In quantum mechanics, if particle is in some state, even if we assume that it is moving, we don't know, but it is in some fixed state with the same energy, so in this case there is no movement from the point of view of quantum mechanics. A movement is when particle change its states from one state to another state. So this is Schrödinger equation for stationary states. As I already mentioned before, there was some hint how this equation can be obtained. Actually, the idea is as follows. Mathematically, any wave is a solution of wave equation. We remember what is a wave equation. Wave equation is Laplace phi of RT is 1 over v squared, and the second derivative of this, when phi is some function which describe a wave, whatever this wave be, electromagnetic, mechanical, and so on. So, if so, we can assume again that f can be separated on coordinate part, which depends on radius, and time part. Then, if we substitute it in this function, in this equation, we will obtain that Laplace phi is omega over squared over v squared phi plus phi of r is equal to 0. Well, this is k squared. Then energy, we say for stationary states, energy is constant. So energy consists of kinetic energy plus potential energy, and it is constant for stationary state. But P is hk, and k squared, which is here, is p squared over h squared, and it is from here we can derive p squared, so it is 2m over h squared e minus u. And in this way we arrive to this equation. So here is, if you compare this equation and this equation and this equation, you see that this term we have here. But again, this is not a derivation of Schrödinger equation. It is just a consequence of the fact that any wave is described by a wave equation. So it was a task for Schrödinger to find this wave equation, and he wrote this equation, and now we use it as a main equation of quantum mechanics. Since a physical meaning of the function, psi function, which is connected with probability, this function should obey some requirements. Namely, it should be continuous, single-valued, and finite. Why so? First of all, because of this sense of probability. If it would be not probability that the particle is somewhere and can be found in all the volume, infinite volume, is 1. So there was such a normalization that if we integrate over all the volume psi asterisk dv, it should be equal to 1. This is normalization of any probability. This is possible only if this psi is finite, and if particle probability of to find particle in any volume should be unique, and so the function should be single valued, and in addition it should be continuous, because it cannot jump from one point to another point in another volume, not being in all volumes in between these two volumes. So the function should be continuous. It appeared that Schrödinger equation has such solutions which satisfy this three mathematical restriction on the function, which follows from its physical meaning. And this equation has such solutions not at any e, but at some specific values of e, which are called eigenvalues, and corresponding functions which can be found as a solution of this equation are called eigenfunctions. Again, this at these values of e, actually these values are values at which system is can exist, and in this at these values solution has this function which are found from solution of this equation satisfy these three requirements for this psi function. Now we will consider some unusual consequence of the wave properties of particles, and this is so-called principle of uncertainty. Uncertainty principle. Sometimes it is called Heisenberg uncertainty principle because German scientist Heisenberg derived it. Well, let's now we know that particles can be considered as waves, and some diffraction should be observed if these waves are propagated through some slits. Let's consider such a mental experiment, because we cannot, of course, perform such experiment, but we can imagine that we have here is some direction of propagation of particles, and this is a screen, and particles, this is x-axis, and on the way of particles there is a slit, and the width of this slit is d. Now what we expect? We expect here usual diffraction pattern, its maximum here at 0, and the first minimum here and here. From optics we know that d sine phi is equal to m lambda, where m is 1, 2, 3 and so on, and the first is m is equal to 1. So sine phi is equal to lambda over t corresponds to this first minimum. So if we look where is phi, phi is this angle. Now look, in order a particle, if we consider that it is wave and particle simultaneously, in order the particle reach this point, here it should have momentum p directed in the direction. So it should go along this way. It's a way to the first minimum. And what is possible? We remember that most of intensity is in the first maximum. So this is projection of px, and this projection of px, if we look at this, can be changed from all the particles should be between this and this point. So the projection of px should be from 0 to p sine phi. This is in order to the particle to reach this screen in this interval. What we know about coordinate of this particle? When particle passes this slit, we know that it passes this slit somewhere in between this edge and this edge of the slit. Not more accurate, we know this. So we know only that it went through this slit. So we know coordinate x only with uncertainty equal to d. Consequently, we can say that delta xx is d. This is uncertainty which we know coordinate. Now look here, we know px with accuracy from 0 to this, so delta px is approximately p, and sine phi we will take from here pi lambda over t. Approximately, because not all the particles are in the central maximum. Some are even farther. Now we know that P is hk. That is h on lambda. Remember that 2 pi h is h. 2 pi h bar is h. And k is 2 pi on lambda. Now if I use this and substitute here, we have that delta px is equal to h over d. But d is uncertainty of coordinate. From this we obtain that delta x, delta px is proportional, okay, to h approximately. If you made experiments in optics, I don't know whether you did it, with diffraction from Goffrey diffraction, you have to know that when this slit is narrower, then this peak is more broad, and this corresponds to our knowledge about coordinate and momentum. If we make this slit narrower, we know about coordinate better, because we know that it is somewhere in this narrow region. But in this case, the momentum is known worse, because this angle of scattering increases. This means that we cannot simultaneously define coordinate and projection of momentum on the same axis at which we measure coordinate with accuracy better than same value of h. This is uncertain principle. This means that in quantum mechanics, accurate measurement of such two values cannot be made at all. So only if we know better one of such values, we know worse another one. When we consider electron in atom, it appears that due to a very small volume in which atom occupy and electron moves in this volume, this results in uncertainty in velocity such large that this uncertainty is of the order of velocity. So we know nothing about velocity. Thus it is not possible to consider movement of electron in atom along a trajectory.